Hello. So how many people do you have there? I can't see.
Nobody.
What? Nobody. Aye. Well.
Oh, one. There's
oh,
one.
Here we go. Oh.
Well, it's raining today. One more. Dr. Dabada and Dr. Sensor and two more are missing. I probably should remind them.
There are three more missing, right? I mean,
Dana's here.
oh, Dana's there. Okay, great.
I have a big jacket today. I didn't know this was 3:30. This is the first time that I, I didn't either. Yeah, I was like, oh, that's 3:38.
Oh, we still have time.
I am.
I just came like this, skateboarding.
Nice. I have more chalk if you want.
What's a funny room?
I bought the chalk that I still need.
Okay. So what do we need? Doesn't matter.
Well, we just need two more committee members.
Or
I hope they're coming.
who's the outside person?
Forgive me for not knowing the name. Yeah, here he go. There we go. Greg.
Oh, Greg. Okay.
Yeah.
Okay. And then
So Greg is here, and then we have
Donna. Is it?
yeah, and I'm so bad with names. Okay.
And Jen.
Hello, Greg.
Oh, hello.
Hi, Doctor.
I thought I was going to make it in live today, so I apologize. That would have been fun. It didn't work out.
There's no portable microphone.
Oh no. So where is this?
Microphone right now it's the camera's microphone.
Oh yeah, because it's the cube, right? I remember if you've seen it. I can watch pictures of it popped up in my memories today. Yeah. He used to fit on my phone like this. Now it's like
So after this, I will put all my committees in a separate room in a breakout room. Except Dr. Badashova.
yeah, how am I gonna participate?
Maybe.
Maybe you have to leave the room and I'll.
Oh.
That's usually what happens in physical environment, right? You leave the room.
That's right.
So
I'm
yeah,
not-
because I have to communicate somehow.
Yeah.
Yeah. Traditionally.
Okay.
Robin's here, but we're still missing.
Have you sent him an email?
Not yet because. Hi, Robin.
Hey there.
Okay. So I think
Okay.
the committee is complete. So in principle, there is nothing that Prevents us from starting, okay? Well, maybe you can still wait for a couple of minutes before everybody shows up.
I would wait. I almost said, Dr. Balashova can leave your room and log in from your phone and join the breakout room, and then I can chat with the rest of the people in person and online.
I can always do that.
Well,
Then I will have to leave the room. Physically.
what will think about it? I have the touch screen on this one, and this one is not a touch screen.
And you can use the pen as well.
There's no pen.
Oh,
I can use finger.
yeah. Weird.
I have to set up so that the projector projects my slides on this, not another. Let's wait at most 2 more minutes, I would say. Okay. 15 more seconds. Wait. I will share my slides.
I think we should start. Okay, just keep the schedule.
Sure. So thanks everybody for coming. It's my honor to present my PhD thesis, distinguishing chromatic numbers for isosceles triangle in choiceless set theory. I'm working in mathematical logic and set theory. So chromatic numbers for isosceles triangles, by which I mean the chromatic numbers for isosceles triangles hypergraphs, and I will define the terms. And I will first talk about these problems in the traditional setting when we have axiom of choice. And then I will go to the logic area when we don't have axiom of choice. And we call that choiceless set theory. And I will tell you what I mean by distinguish the chromatic numbers. I will try to start slow because we have no math people. So introduction. In a math talk, we always start with definitions. So definition for Kn positive natural numbers. A hypergraph gamma of arity K on Euclidean space R to the n is a collection of sets of size K whose elements are in R to the n. Or you can just say it's a subset of R to the n to the K. And elements of gamma are called hyperedges. And right away, I want to point out the example of isosceles triangles. I think I can draw here by my finger. You know, you have a R squared XY plane, if you see well. You know, here is an isosceles triangle with vertices ABC, and there are many more. They are all over the place in the space. And the gamma, I call that gamma 2 on the two-dimension space. That will be a collection of the triangles. The vertex of triangles. ABC is one of them, and there are many more. So we put them together in the collection. But we don't typically notate like that. I just want to point out this example. So that's the isosceles triangle hypergraph. A graph, it's simpler. It's just the one with arity 2. Wonder how I erase everything at once. For example, we can have say on the real line. Zero, 1, and all the way to plus infinity and negative infinity. The rational distance graph is a collection of all the pairs such that the distance between them are of rational distance. For example, the pair 0, 1, that's in the graph because they are 1 apart. And you can have, 1/2 and 10 halves over there. They have rational distance. So all those pairs will be in the graph. An algebraic hypergraph is a hypergraph that is defined by polynomials with real coefficients and unknowns. Our isosceles triangle is in fact algebraic because we can describe that, you know, probably. Oops. You say those two sides are equal, and that would be an algebraic equation if you write down the distance formula. And oh, I don't have to clean that. Now, colorings. So gamma colorings, when gamma is a hypergraph or graph, is a possibly partial map C on the space R to the n, such that there's no gamma hyper H on which gamma is constant by C. So for example, if you, again, you are on the plane and you want to color, you put a color on every point on the plane. And whenever you see an isosceles triangle like that, you can't put all 3 points blue, for example, and that would violate. That would be a constant. That would be monochromatic. You have to change one of the color to maybe red or something. If there is a total gamma colorings such as the range is uncountable, the chromatic number of gamma is countable. Otherwise, the chromatic number of gamma is uncountable. And we can also talk about if you can color the graph or hypergraph by a finite number of colors. If you have a finite graph, sometimes you can do that for infinite graphs. But we are mostly interested in distinguishing between countable chromatic numbers and uncountable chromatic numbers. And we realize that the colors they don't matter anymore. We don't care what colors we are using. We just care how many colors we have to use. We are trying to use as fewer colors as possible. So we may as well color every point by natural numbers, 0, 1, 2, 3, 4, and so on, or any other set of objects which countably many, if we want to try to color them countably. Define that gamma n will be our main character today. That would be a hypergraph of isosceles triangles on Rn, the m dimensional. So that's the progress that people made in last century for n positive natural number. The chromatic number of gamma n's countable. Erdős, one of the greatest mathematicians in 20th century, conjectured many of the theorems of this type and proved many things. So the n equal to 1 case was proved by Erdős and Tutani in the year 43. By the way, the one-dimensional case looks like that. So that's one-dimensional. You are on the real line, and you have 3 points, and those are equidistant. And you don't want same colors for all three of those. That's a problem for 1D, and we have higher dimensions. And as it gets higher, it becomes more difficult. So those results, they are done using the axiom of choice and the continuum hypothesis. And I will say what they are. Later, Schmerl proved the NEN case without continuum hypothesis. That was pretty big breakthrough because we use less assumption. So what they are? So most mathematicians, they take axiom choice and continuum hypothesis for granted. But in fact, as logicians realize, they are not always true. Their truths depend on which model we are in. So axiom choice, AC, says that for any set of sets, non-empty sets, there is a choice function or selector F, such that it basically picks each element of that. So picture would look like you have a collection of bubbles and so on. They are non-empty, so there is something in the bubble, and you can. It says there is a function. There always is a function that you can pick one element out of each. For any such set of sets. That's AC, and continuum hypothesis basically says the size of real numbers is of the first uncountable cardinality. Just a few more results. Schmerl proved the theorem for equilateral triangles. And another interesting result, Erdős and Comia in the 90s proved that fixed n, the statement that the chromatic numbers of the hypergraph of right-angled triangles Rn is countable, that is equivalent to the continuum hypothesis. Given a model, they will be both true or both false at the same time. And the final one in the history, well, not a long time ago, Schmerl provided a complete classification of the chromatic number of a given hypergraph. And I won't read those just to save time. Any question before I get into logic stuff? So logicians like to ask, those are the results of axiom choice, where at least you have to have, people use that to get the results. And so what if we don't have axiom of choice? Can we do a parallel categorization? And we observe and expect that it's much more difficult. We ask such question, let gamma prime be hypergraphs, possibly different hypergraphs. There exists a countable coloring for the first one. Does it mean that there exists a countable coloring for the second one? It turns out, and we expect that the answer is no for many cases without accent choice. So that's the interesting part. If we don't have accent choice, when we do have accent choice, those hypergraphs that we are interested in, including the isosceles triangle hypergraphs, they just have chromatic numbers all at the same time. But now, without AC, we can tell them apart. All of a sudden, many of them, and still many work to be done, but we conjecture such thing. So instead of AC, we consider DC. The action of dependent choices. It's a fragment of action choice that on which real analysis can be developed, possibly without paradoxical AC structures. There exists a set of reals that is not the big measurable. A theorem that in fact, is pretty crucial for my result, we will use is that over ZF, DC is equivalent to the Bayer category theorem for complete metric spaces. And I will mention that again when we use that in my proof. Any question? So here comes my result with ZF and DC and any accessible cardinal. That's the axioms that we need. It is consistent that gamma 2 has countable chromatic number while gamma 3 has uncountable chromatic number. And that's how we distinguish them. We prove that by invent a model such that the statement holds. Positive. So I call there are two parts. Positive part, invent a balanced coset that will add a countable total coloring for gamma 2. So we force there to be a countable coloring in the resulting model. And negative part, you just can't have the coset to be too strong that it adds anything that we don't want. So we don't want it to add a countable coloring for gamma 3. So it has to be fine-tuned. Now, to achieve this, we need to investigate geometric, algebraic, or combinatorial differences between them. And I will be talking about that today. Any question before I go into the techniques? So before balanced forcing, we need Solovay model that's invented in 1970. Theorem by Solovay from a model of ZFC and inaccessible cardinal. One can build a model of ZF, DC, and all sets of reals, the big measurable and bare and perfect set properties. That's one of the earliest independent results that is was pretty big. Just to put the definition here, start with a B ground model of ZFC and kappa in inaccessible cardinal, and let PC be the collapse forcing. With kappa, and take a generic filter G, then the symmetric Soloway model denoted as W is HOD, which means hereditarily ordinarily definable sets from V to ground model elements and omega to the omega, the bare space or the reals can replace that. And computed in each. It's fairly complicated, and we will take the complexity further because we will force over this model, and so it will be even more complicated. I will see if I have time to draw a rough picture about these forcing extensions, just to be better than no pictures. So with W, we can do the so-called balance force, which is pretty new. It was invented in the new book Geometric Set Theory by Larson and my advisor W. And that's a powerful tool to prove independence theorems in choiceless set theory, with a form that is consistent relative to the plus DC that phi is true while psi is false. And phi and psi, they are sigma to one sentences. It just means they have certain format and complexity. And they are typically consequences of ZC or ZC plus CH. So if we always assume AC and CH, they're all true. So we have nothing to do. But without them, we have a lot of works to do. And we have lots of independent results like that. Quickly, examples such as saying G graph or hypergraph has countable chromatic number is sigma to one sentence, and X has a basis is sigma to one sentence, and the continuum hypothesis as well, sigma to one. Any question before I define my process that I will pause? It's forcing, so we need a poset, and poset stands for partially ordered set. It's a set of elements that we call conditions. So it's a set of conditions with ordering less than or equal to 4. Whatever symbol you like, but the convention is less than or equal to. It needs to satisfy a few things, such as, P is just a set of countable approximations of the countable colorings for R2 in our case that we want to achieve. We can't do total coloring, but we can approximate from our ground model. They are ordered by strengthened reverse inclusion. So one extend another, shortly speaking. P is transitive and sigma closed. And P is analytic, which says about its complexity. And the support of P is a countable real closed subfield, and it turns out to be very useful in any term in my proofs because of quantify elimination of real code subfield and model complete. And the last two, this one says you can always extend. Just draw a rough picture. So suppose you color a bunch of points in this bubble, and you want to extend to a new point outside, and you can do that. You can always find a coloring with more information that will color that point, and it's still a color. So no monochromatic hyperidge is created by doing that. And last one, we call such property as amalgamation property. It's when you have two of them. You want to, when they are gray in the middle. And say there's a point outside, you will be able to extend to a bigger coloring that colors that point outside. And this needed the most work. This is the most difficult part to achieve. So that you can sort of get the feeling that we are approximate the coloring that we want to get by those things, and you want to be able to extend to a bigger one nicely. Now that's my definition for the flow set. I fix an ideal. That's in a good one in a sense. That it will serve for a collection of small sets. And when we color, we will put colors in I, in a sense small, so that we don't run out of power. So P is a collection of conditions. Support of P is a real code subfield, as we required. And P is a countable government to coloring. And 3, I call that symmetrical colors requirement. And I can draw something. In your domain, you have 2 points, and you see you see a line right in between. Which is a perpendicular bisector of that line segment. So the pair of points are symmetrical with respect to them. And you may see there can be another pair of points, and they are symmetrical with respect to the same line. And you can have more. You can have, in fact, infinite many of them. And the problem is that you may run out. So every pair of them have a color, and when you extend, if you want to extend the coloring to a new point that is not colored on the line, you may run out of color. If you have all those pairs of colors, they all used up every part of the color. And that's problematic, because every point with each pair of those points, they will form isosceles triangles, and we don't want any of them to be monochromatic. So this item 3 is to say, well, those colors are in I, which means small. And when we extend, we can have, we always have, in fact, lots of options there. So after 1, 2, 3, we have a bunch more for the orderings. The main art is happening in ordering, in fact. 4 and 5 are straightforward. You want to extend, you want to agree with the smaller one. And 6, 7, 8, this one is close to the S we had in item 3, but this one just says it doesn't grow, so that we have sigma closure. Probably will. Don't have time to go to the details. And the 7th, it talks about circle, because the circle is another place that isosceles triangle is found. So we want, avoid center scalar in some way to be able to extend our colors. And item 8 is the most mysterious one so far, and it did take the most amount of work. It is to achieve the amalgamation property, so that output is balanced. And again, I will come back depending on the time for those. I will prove the theorem. Again, kappa is inaccessible cardinal. Then there is a model of wave plasticity that in which gamma 2 has countable chromatic number, while for every non-Minger set A in the dimension 3 Euclidean space, A contains all vertices of the isosceles triangle. And this will do the job for the main theorem to say that there's no countable coloring for the isosceles triangle in R3, because if you give me any arbitrary, possible candidate for the coloring, I look at the partition of the space by the pre-image of every single color, so that the partition of the space is such that every part gets the same color and it's a countable partition. Now use DC. Remember, the DC is equivalent to Bayer category theorem, that the one of the piece will be non-Minger. We can find one piece with non-Minger, and unfortunately, there is a triangle. There's an isosceles triangle, and they all have the same color because they are at the same piece, and that function fails to be a copy because of it. That's how we argue the failure of having a countable color. So start with W, the symmetric Solovay model derived by kappa. The model we need is a P extension W. The P is a few pages ago that we spent with. That's kind of lengthy definition, and we get WG such that gamma 2 has countable chromatic number by our construction of P. We got all the countable approximations, and then we take a generic filter G, and that will bring a total coloring for the whole space by forcing. I want to talk more about the negative part. I mean, I'd like to talk all of those, but we have limited time. how do we, find the isosceles triangle in the non-meager set A for every, in fact. So now to do that, here I will try to quickly go through the mechanics of doing that. And it turns out that for other independent theorems, this negative part, the mechanics looks the same, looks pretty similar. The details are different depending on what you are doing or what hypergraphs you got. But here we go. A P is a condition and tau is a key name for non-meager subset of R to the 3. We want to find a gamma 3 hyper H and the condition to force the hyper H E to be in that set, and we would be done. So making use of the W, its definability. Remember, we had a HOD and stuff, so that parameters are found in the intermediate model, so that we can get we can force starting at VK. Again, quickly going through those things, and in VK, let P bar be a band spatial condition. And here is how we force a point. So we want to force 3 points. 3 points, they will form isosceles chain. Before 3, I will tell you how do we do 1. So we shoot 1 point by Cohen coset P of R to the 3 consisting of non-empty open sets of R to 3, and by reverse inclusion, it will shoot X generic dot in the space. And I claim the one highlighted in red has to happen by a bunch of forcings before that, iterated forcing. You don't have to try too hard to read that. So let me quickly argue that it has to happen, just because if it doesn't, it's going to contradict the assumption that tau is forced to be non-linear. It just, the definition of non-linear that I didn't give you, but you can ask me afterwards. So that's what I claim for 1 point. Now, how we do 3 of them? So P sub gamma 3 bar, I put the bar because you will see later. And that is going to Cohen forcing of like that will force, and forces 3 points atop triple, and that will form an isosceles chain. And inside the same O that we had in the previous page, so that they stay, they are forced by this condition O. So and we have the 3 models. E has 3 points, so there are 3 X's, and a bunch of observations, and that I have to skip, but I will come back to the details. There's a key claim that I will come back. So with the claim and the observations in the previous page, let me just say the finish line. Now let Px to be a tau evaluated at each X, there are 3 X's. So there are 3 conditions, and then we have this amalgamation of 3 of them, so that we can have a lower bound Q. And we are done because Q will force gamma 3 hyper HE to be in the non-linear set tau. That tau will become a non-linear set. So we are at the finish line, but we are going back at some details. There are lots of details, but I want to point out a few. This part, I don't think I have time. It's still interesting. It's positive part, and that's about how how P has an amalgamation property, and how is that make P balanced? Because being balanced is the biggest deal when we invent the process on the CH. We will need CH in the middle when we force. So let me jump to look at the details for the negative part. Open maps and hyper-H forces. So here is my gamma 3 bar. It's just ordered version of gamma 3. The middle coordinate is a pivot point. And we check that it's d delta, complexity is g delta, so that it's a Polish space, so that we can do a coherent forcing with it. And we need, in the middle of the proof, we need lots of open map propositions. And to achieve open map, I would just state that whenever the hypergraph is invariant under similarity, then we can have the projection of G, or G of well, here is arbitrary everything, but project to any two coordinates is an open map, and you can check. I'm sure any of you can check the isosceles triangle hypergraph is invariant under similarity. If you rotate, if you flip, if you shrink, it's still isosceles triangle. So that's pretty intuitive to see that it's invariant under similarity. And by the composition, we have corollaries saying, I just said the example gamma 3 bar, and that will give us mutually genericity of inside our forces, and we need that all the time in my proof. Again, here's a repeated claim that when you let me give again a misleading picture, but better than nothing. Again, what we are doing is to shoot an isosceles triangle in R3. And we want to guarantee that we didn't by accident add any no such in R2, because if there were, we will have a big trouble when we amalgamate our colorings for R2. So it's nice to not have that. So that's the claim. That's what the claim is saying. Let me label the ground model. It's okay, but many things to be labeled. how is this proved? Proof by contradiction. That's a pretty common strategy that we use every day. Suppose there is such triangle, then something will go wrong. Why something will go wrong? Because we consider the following definition that you don't have to read. I will draw a picture, give you a sense about what it's saying. So isosceles triangle. So this one isosceles triangle. I duplicate one of the vertices. So there's, by the way, we count from 0 as any other logician. So 0 is coordinate, duplicate by k times. In fact, I've duplicated by 4 times. But duplicate, twice looks like that. This is a duplicated. So this is a new hypergraph made out of the older one. The one more vertex, and this vertex, this is isosceles triangle. And that will be, and I'm gonna do that 4 times to make it work. And we will do a cosine forcing of this. And if we assume this problematic assumption, which is opposite we want to prove, something will go wrong if we force with this thing. So the key, here's the key. I made a definition of stable against 4 vertices. Because of this fact, we have a bunch of, again, no open projections, and as a result, we have mutually genericities of part of the generic tuple. And that's a key, the keys for going through argument. So what is stable against k vertices? The definition is that long, but don't feel like you have to read it. I will again just to show you the sense of it. So again, we have in R3, 3 dimension in 3D. We have 1, 2, 3, 4. And I don't want to draw every single one of them, but they all connect with 2 other points as a isosceles triangle. So I duplicate by 4 of them. I plan that whenever you apply, you move those 4 points. You move them by arbitrary directions with arbitrarily small amount. So if you draw a little bit, you move this direction, move this that direction, move this direction, move this that direction, arbitrary directions and a small amount. Then that's gonna result a twist, not really twist, stretch, shift, rotation of the whole space of R3, including those 2 points circled in yellow. They will move with the space. And after everything is moved, those 4 points with another 2 points, they will stay as such duplicated hypergauge. So they will stay as a hypergauge. it's formally, there's a continuous function of psi that from the neighborhood, that will represent the bunch of the vectors. And it maps to the similarity, in fact, similarity groups of Rn continuously. The continuity needs proof. But this is what it means, and it probably, well, actually, it's not that obvious to see. And let me claim that it is true for K is at most 4 for the gamma 3, while the K is at most 3 for gamma 2. So K is less than or equal to 3 for gamma 2. And that's the key we tell gamma 3 and gamma 2 apart. Is here. If you ask what's the one,
Okay, how you did it. My first thought was to use an N, so I just,
Yeah, so I just switched it to N
Yeah.
plus M.
it's,
I just muted. And that's all I have to say for my talk. And thank you very much for coming.
Yay. Terrific.
All right. So are there any questions?
Yeah, Dr. Ray.
Yeah. Why didn't see anybody jumping to the microphone? So, well, I'm not going to try to ask you a technical question. As your outside member, I want to ask you a sort of non-technical, a general question about the context of the work that you're doing. So one of the things that I notice about the dissertation is that it's very internal. So when you set in and you give us some of the historical background and so on, what we learn is, for example, that, well, these structures and working with these constraints, there's been a lot of interest in that, and then we kind of go from there. So what that says, of course, is that some other mathematicians, perhaps of some note, have engaged in some endeavor there. So it tells us that they've been interested in it, but it doesn't tell us why it's of interest. So the sort of contexting that I'm just going to invite you to say something about is why this sort of work is of interest. Not, I know that other mathematicians have been interested in it, and maybe it's the sort of thing that one needs to say to someone outside of mathematics who might be thinking about paying you money to do this kind of work and wonder why.
Yeah. One of my goals for today is, to convince you the interesting and the meaningful part for the work without accent choice. So as the one I mentioned was that I'm not sure where they are. So for my stuff, coloring hypergraphs or graphs, under accent choice, they will be all countable all at once. And and that's it. But without action choice, that's where everything is happening. We can tear them apart about the chromatic numbers, and one doesn't imply each other. One doesn't imply another anymore. So that's this question, and also the why one doesn't imply another is also interesting. And what I did was one of the answers, one result for such question. With this, they all true, so they imply each other because they're all true. But now it's pretty colorful. Picture that we can see between the chromatic numbers.
Let's see if I can just try a follow-up. It must at least almost be an understatement to say that there are uncountably many structures and which could be investigated. So,
Sure.
We'll grant that we know that set theory is important, but what is the context in which it is important or interesting to pursue what we can show without the axiom of choice, for example? And that's part of, I mean, that very broadly is where you are. I mean, you're doing stuff about coloring, but I mean, and it's like, okay, well, if we only have this, then what can we show or not show? So okay.
Yeah. So
independence result. I get it. So
I was gonna say independent results between
yeah.
the sentences, and that's a lot of fun to me, at least.
Okay, fun. Yeah.
You see, the one doesn't imply another in a general sense.
Okay, thanks.
Thank you. Yeah, also, I think, for non-logicians, I think that helps. That would help to understand, the pure math part better, because we can tell them apart. We can tell the differences, for example, of getting a kind of a coloring, and we can things like also see that DC is equivalent to bare category theorem for complete metric space, and I think that's a wonderful thing to know. With AC, axiom choice, they are all true, but without it, we see, our old friend bare category theorem better. We see it better. It's actually equivalent to dependent choices, and we wouldn't be able to see that if we always have AC. So that's in anything. So I think it gives the better understanding for well-known theorem for general mathematicians. I suppose they would want to hear that.
Yuxin, just to clarify, most of the introduction you were crediting the authors of the theorem. So this theorem about the bare category theorem. So who proved that?
This is in the book of
Checker?
no, probably there, yeah, too, but
Okay, just checking. All right. Okay.
I found in the 1977.
Okay.
Dr. Blair.
Okay.
Start with last name BL. I didn't
Yeah. Okay. Sure. But
because I figured that
Howard, maybe. Yeah. Okay.
I couldn't find the origin.
Okay. So, what would you say is the main result that you have in your dissertation? You go down and highlight that for us.
Yes, right here.
Yeah. Okay. So I would say this. To me, this is like the. Why did you climb the mountain? Well, because it was there. I mean, this is such a challenge. When before Yindra started working on these things, you would have thought it completely impossible that you could prove such a thing. Okay, it's very impressive to on a technical basis, of course. It's very, very impressive that he had such specific conditions. And these are interesting. I mean, these things are living somehow in unless I lost it somewhere. They're living in R to the N, right? They're kind of fairly natural structures once you get your head around having more than 2 dimensions, I guess. Yeah. So and it powerfully extends the previous results of with people like Erdős and Schmerl. So I find it very nice.
Yeah, thank you. Yeah, it's also a big luck of me to work with my advisor to, get everything from this book and do more fantastic things on top of that, including this one. And of course, the next thing is to go higher dimension. And I wanted to mention that I always forgot to mention the negative part will pretty much we already know it's pretty much like that for any dimension, but the balanced part for adding a coloring, that's where I'm stuck right now. But we suppose it will we can do that. We expect to be able to do that. In higher dimension, it's just so easy to run out of the colors when you extend, when you amalgamate, because you have much higher freedom of wiggling around in a higher dimension of your triangles. And but I expect there is a nice general way of handling that in higher dimension.
All right. So are there any other questions?
You already answered my question.
Oh, okay, I already answered. Any other?
All right. So I think if there are no other questions, then what we should do, we should probably leave the room and
I thought somehow put you all in the breakout room. I mean, my committee.
Yeah, but we have Donna here.
Donna, yeah. So that won't work. Yeah.
So unless Donna can log in somehow, and, but at any rate,
We
You can just go, just go outside.
Four people of us will.
Yeah, but in fact, I would have to ask everyone everyone who is on Zoom to leave. Okay.
Well, I will.
All the audience, yeah.
Let me give you a breakout room.
The non-committee.
At the non-committee members, and also the recording should be turned off. Okay, which I don't think I can do it. Okay.
Okay, let me do that first. Let me turn off the stop recording.